What is the next prize?
The IOCCC prize in solid body physics.
Yes. Not solid state physics, solid body physics. That could give you a clue. And perhaps the author may or may not know this refers to their submission, which is an amazing piece of code. But let's see who won this coveted prize in solid body physics.
And the IOCCC prize in solid body physics goes to Yusuke Endo from Japan.
So this is Mr. Endo's world record 20th IOCCC winning entry, second of the night, and an impressive piece of code, an impressive piece of computation. This is just astounding what this code does. But let's see, how do you actually compile this piece of code? Now, you can compile it, and we compile it, you can give it these parameters, and we'll explain what those parameters are. We give you two variants of this thing, prog and till, but it's the same prog.c. And when you look at the source code, it's self-documenting. You see there's this little spinny top thing that's sitting on a base. And it even tells you how to compile and what to do there up in this comment. It's very helpful self-documenting. And even gives an IOCCC for the current year 2025. So it's a helpful thing. And you look at it if you look at it in clanged formatted stuff, you see here's the main down here, and it has a set of various functions and variables, not having macro set, but a straightforward set of functions. But let me tell you, there's some magic going on in this thing. There is this setup of stuff where you read in a file, and then you down here have this iterator with a micro sleep while it's doing some very interesting computation and output that is pretty fun to see. So let's see what this does. But before we do that, I should mention it comes with a number of text files, various objects, bottles, sticks, cylinders, vases, eggs, halos. And when you compile, you can compile with a number of parameters. So the make file has these parameters, talking about the width and the height of what you're doing, the time step, a coefficient of restitution, which we'll talk about in a minute what that does. There's a friction and a speed and a tilt. And when we see it in operation, here it is. So this is an example of one thing. You see a spinning top being emulated with the speed there on the side in RPMs. Here's a halo being printed. Here's a cylinder that is rotating. Here is a vase, and you see the vase is in the process of tipping over. Here's an umbrella set. Here's a bottle that's beginning to spin, and here's a case of a bottle inverted. Now, what we did for each of these is here's an egg that ends up rotating itself along its axis, and another top spin. And you see it goes through the process. It's showing you the rate, the RPM speed. It's doing the computation. I played with the parameters to have these things roughly do finish at around the same time. You can see that it falls over. It's showing you the backside of things as these things come close to a rest. You see there's the egg about ready to fall over and whatnot, showing you where it is. Here is the classic tipple top. and starts off at a very high rate of speed. Due to its shape, it will actually invert properly, stand on its edge, and spin on its axial axis. And you can see in the side there the spin rate as friction causing it to slow down. So it's modeling the speed, modeling the axis, the inertial angular momentum, and you can see the frictions causing it to dance and slide over to the side. As it slows down, it then falls over, reinverts itself. You see the inside is modeling the inside of it as well, and comes to a rest.
Wow. Just wow.
So it starts off with a text file that's basically gives you the shape in ASCII. If you look at it, it's just a simple text file with some parameters. By the way, the source code is also, you can twirl the source code and it sees the outline of that top and spins it as well. And you can play with it in terms of those parameters about the restitution and so forth. I don't know. Any other comments we have for this amazing entry?
No, I don't think so.
I mean, the things like gravity.
It's impressive, but I think it's. I mean, what can you say? But it's pretty obvious why it's impressive, I think.
Yeah, and so that restitution is how, for example, we think it's how, for example, the things like gravity come into play, as well as fluid. I'm sorry.
I think that was Leo.
I wonder if restitution can be treated as anti-gravity.
Yes.
Yeah.
Sort of the anti-gravity stuff, resistance to it falling over. But it also, as it's just doing it in real time, you can see inside the notion of what's inside outside. So you saw that it gave you some notion of the shape as well as computing. The way it computes the RPMs is also interesting to find in the code. Really quite a tour de force, outstanding piece of computational physics. Well done, well done, well done. Thanks for watching. And before you go, please like and subscribe and check out the social media links in the description below. And if you like, you can support us on Patreon to help us bring you new content so you may enjoy our favorite universe even more.